Okay, in last lecture we have seen unbiased estimator of population mean as well as population total under the method simple random sampling with replacement as well as simple random sampling without replacement. Today we'll try to verify these results with numerical example. In a population of 5 units having values 3, 7, 5, 8 and 10. This is only for illustration. There is a population with 5 elements taking these values. Draw all possible simple random sample without replacement of size 3 taken from 5 elements and verify that sample mean is unbiased estimator of population mean. Hence, obtain unbiased estimator of the population total. So, this is a simple example to verify the results what we proved last time. See the solution. In this example, we have population with 5 elements. We want to draw sample of size 3 by without replacement. It is given that capital YI takes values 3, 7, 5, 8 and 10. So naturally population mean will be the total of these all values divided by number of values in the population. So my answer of the population mean is 6.6 and population total is 33. So I have the knowledge that population mean is 6.6 and population total is 33. Let us see now how the sample mean is unbiased estimator of population mean for this example. The following table gives possible sample of size 3 by SRSWOR. When I have a population of 5 elements and I choose 3, so 5 choose 3 will be 5 factorial, 3 factorial, multiply 5 minus 3 as a 2 factorial. So when I simplify this, my simplification will be 10. So it says that there are 10 possible samples of size 3 drawn from 5 elements. Let us see what are that 10 samples. So these are the values under study. So my first sample will be 3, 7, 5, 3, 7, 8, 3, 7, 10, 3, 5, 8. So these are the list of 10 possible samples of size 3 elements with respective values by using this combination result. Selecting 3 out of 5, 5 choose 3, answer is 10. Now for each of the sample, I will get a sample mean. Total of these values divided by 3. Total of these values divided by 3 and so on. So these are the 10 sample mean with us. Now therefore, expected value of y bar. I want to prove sample mean is unbiased estimate of population mean. So this is equal to summation I1 to 10 y bar I multiply probability taking the value of y bar I. So I have 10 samples To study population, I pick up one sample at a time. So chance of selecting particular sample is 1 by 10 for every sample. So it will be y1 bar multiply 1 by 10 plus y2 bar multiply 1 by 10 and so on. Now 10 is a common constant multiplier. So the numerator will be y1 bar plus y2 bar and so on. The total of these, that means total of this column. If I make a total of this column, it comes to be 66. Divide by 10. Answer is 6.6. So what is 6.6 here? 6.6 is a capital Y bar. Therefore, this numerical example proves that expected value of sample mean is nothing but your population mean. Now, if I multiply capital N to sample mean, then I will get a population total. So N is multiplied, expected value of Y bar we got 6.6. So 6.6 multiplied 5 is 33 and 33 is nothing but total of population values. So it is a very simple example which proves the result that sample mean is unbiased estimator of population mean and capital N multiplied sample mean is unbiased estimator of population total. Let us go ahead. We have this repetition. Variance and standard error of unbiased estimator of population mean. This is a new topic. What we did before, it is unbiased estimator of population mean and population total. That is the sample mean is unbiased estimator of population mean. Capital N multiply sample mean is unbiased estimator of population total. Now what this topic tells you? This tells how to get calculation of variance. What is the variance of unbiased estimator of population mean? That means under this topic, we'll try to find variance of sample mean. And after getting variance of sample mean, take the root that is called as a standard error. So standard error is nothing but standard deviation. Let us proceed one by one. Suppose I apply the method of sampling which is a with replacement. What will be the variance of sample mean? Let a random variable AI associated with the ith unit of the population denotes the number of times the ith unit occurs in the sample I1 to N. That means what? AI will be 1 if population element comes in the sample. AI will be 0 if that particular population unit not coming in the sample. So AI is a binary variable. Just like yesterday I told AI equal to 1 if ith population unit comes in the sample. Otherwise it is 0. So it takes value 0, 1, 2 up to N. The joint distribution of A1, A2 dash dash AN is the multinomial distribution as below. Just now in other paper, I taught you multinomial distribution. The formula of multinomial distribution is n factorial There I wrote x, here I wrote a1, a2, an into 1 upon n raised to n is the probability. 1 upon n multiply 1 upon n multiply 1 upon n every time 1 upon n, it is repeated small n time. So I write simplified like this. Sum of AI is sample size. For this multinomial distribution, we have expected value of AI n upon n. Variance of AI is n into n minus 1 divided by n square I1 to n. Covariance of AIAZ minus n divided by n square if I is not equal to j1 to n. This everything is a result of multinomial distribution. We rewrite the sample mean y bar as y bar equal to 1 upon n summation I1 to capital N AI multiply yi. By taking expectation of both sides and using this as a result, we get E of y bar, E of this entire term. 1 upon n is a constant, expected value of summation ai yi. Expectation goes inside for random variable. This is the fixed values. So E of ei. But what is the expected value of ei I wrote? It is n upon n. So n and this outside n get cancelled. It is summation yi upon n, that is y bar. This is the alternative proof that sample mean is unbiased estimator of population mean in case of with replacement. What is the next step? We want to develop variance of y bar. This is the proof for sample mean is unbiased estimator of population mean under with replacement. This we did before also, but by other approach. Now see variance of y bar equal to variance of 1 upon n summation yi. Now when I took constant outside variance from your first year knowledge, 1 upon n taken outside with a square number. You know, in your first year, variance of A multiply capital X is A square variance of X. So whenever you are taking a constant outside the variance, it is taken by square. Variance of rest term, summation I1 to n ai yi. Look the change. Here I write a small n, here I put a capital N. But this small yi written as ai multiple capital yi. So I write this sample quantity in terms of population quantity by using ai as an indicator variable. If this population unit come in the sample, ai is 1. If this population unit not coming in the sample, ai becomes 0. So this term, which is a sample quantity, and this is a population quantity, both are giving same answer due to this AI. AI is 1 only for those values which are in the sample. Otherwise, AI is 0. So this total and this total one and the same thing. Next line, variance of sum. Again, this is one more result from your first year. You recall variance of x plus y. We proved variance of x plus y as variance of x plus variance of y plus 2 times covariance of xy. Now here I didn't write 2 times. So where this 2 gone? This 2 gone in this summation. I not equal to z. That means I can say variance of x plus y is variance x plus variance y plus covariance xy plus covariance yx. That means that 2 is written separately addition form. I not equal to z, but 1 2 and 2 1 will be written here. That's why this 2 is dropped. Now what is the variance of AI that I put result here to be remembered? N into n minus 1 by n square. So I replace variance of AI is this, yi square as it is. Double summation covariance AI is a minus n upon n square. Again this result you have to remember, yi multiply yz. Now this term is going to be simplified for getting the answer of variance of y bar under the method, what method? With replacement. Let us try to simplify. So this is totally constant, put it out. This is constant plus become minus outside. Double summation yj I not equal to z. Sum of yi square. Now here the one thing is not scanned properly. I write this sum of product as sum of yi square minus sum of y square. How I write this? It is written by using a simple result. What result? x1 plus x2 whole bracket square. How we write? We write x1 square plus x2 square plus x1 x2 plus x2 x1. So if I want to write sum of product, how I will write that? I will write left hand side is x1 plus x2 whole bracket square, that is here sum of square, minus from the right hand side x1 square go to the left with minus sign, x2 square go to the left with minus sign. So this is summation yi square. So sum of product written by this way. Now what is the next? This continue. This is also continue. This is continue here, multiply.
Excuse me, sir.
Yeah.
Please can you repeat the step about x1 and x plus x2 the whole bracket square?
That's correct.
I
That's
did not
correct.
get that.
Okay. See now, I'm trying to write this sum of product. I want to write this sum of product in another way, which is equivalent to these two. What is here? It is sum of yi square. Now this is sum of product. Suppose you take a rough page with you. Are you Nida?
Yes, sir.
Hello? Take the rough
Yes.
page with you.
Yes, sir.
Right bracket
Okay.
x1 plus x2 whole square
Okay.
equal to,
Yes.
what is the expansion of this?
x1 square plus x2 square plus 2 x1 x2.
Good. Now I want to write this 2 x1 x2 all on one side. So
Okay.
you take this other side. So what will be that? That will be sum of x1 plus x2
Hmm.
whole square and minus square of x1 minus square of x2.
Okay.
Are you getting me?
Yes, sir. Yes, I got it.
Yeah. So the one side is sum of product
Yes, sir.
and other side is this quantity. Both are
Okay.
equivalent.
Yes, sir.
Do you get me?
Yes, sir.
Good, good. So now what I do next, I multiply this minus n by n2 square with this term. This minus and this minus become plus n upon n2 square sum of y square, which was missing here. This quantity is there. This is there. Get it? So now next, what I did, this sum of y square, this sum of y square is the same quantity. So I will take a common. So what is the common? N into n minus 1 n square plus n upon n square. So this is going to be simplified. Answer will be n minus 1 sum of y square, because you can see easily this n by n square, this n by n square will be out and this n minus 1 will be balanced with sum of y square. This n by n square is out. So summation y square will be here and this rest part sum of y square will be balanced. I repeat again this n upon n square, n upon n square, n upon n square totally out here. So this is n minus 1 sum of y square minus sum of total y square plus sum of y square here. You can make correction in your notebook. So this is n cancel with square. So 1 by n multiply n square. Sum of y squared n minus 1 and here this is plus 1 because this is taken common. So n minus 1 plus 1 minus sum of y square. This minus 1 cancel with plus 1. So you get n times summation yi square. And what is sum of y in terms of mean? Is it n time y bar. So sum of yi is written as n time y bar whole square. So next line, square inside n square y bar square, n times sum of y square. This is 1 upon n square. This is 1 upon n. This n taken will be out from here and here. So sum of yi square minus n time y bar square. Summation. Now this you know from first year. This is the simplification of this quantity. Summation yi minus y bar whole bracket square written like this. So finally what I got, 1 upon n small n multiply capital N, and this is nothing but by your notation what I had given yesterday. It is n minus 1 time s square. You can see your notebook if it is with you. This is the notation given yesterday. Mean sum of square. Therefore, variance of y bar n minus 1 divided by small n capital N s square under what method? Simple random sampling with replacement. This is the end of your topic. What topic? Obtain variance of sample mean under with replacement. So you have to begin from this onward. What is above? It is a notations, formulas to be remembered for derivation. This is not necessary part of derivation. So B, remember, variance of sample mean under with replacement is capital N minus 1, small n multiply capital N S square. Also we have population variance sigma square, which I had given 1 upon capital N summation yi minus y bar whole square. Again, this quantity is there, you can see. So this is nothing but n times sigma square, n times sigma square. So I replace there. So this n get cancelled with this n. So variance of sample mean under with replacement is sigma square by small n. So you have two results with you now. One, variance of sample mean in terms of S square is like this. Variance of sample mean under with replacement in terms of population variance. These two things are separate. By assuming variance of ith variable sigma square, we have standard error of y bar is a root of variance of y bar. So just take a root of this quantity. So sigma by root n. Or if you want to write in terms of S square, standard error of y bar with replacement is root of variance what we developed. This much. Take the root of this, that is called standard error. This end of the topic under what is the variance of unbiased estimator of population mean if your sampling method is with replacement. Now the same topic, variance, sometimes standard error of sample mean, but method is without replacement. So if you change your method, what will be the variance of the sample mean? What is the another name of sample mean? Another name of sample mean is unbiased estimator of population mean. So to confuse the student, the question may be indirectly like this. Obtain variance of unbiased estimator of population mean under SRSWOR. So it is the one and the same thing. Unbiased estimator of population mean, that means sample mean. So we want to get variance of sample mean under without replacement. What we derived, it is for with replacement. Now we repeat for without replacement. Very small change. Let us define indicator variable AI. AI is 1 if ith unit included in sample. When I say ith unit, that means ith population unit. It is 0 if it is not included in the sample. And this indicator variable is for entire population, taking only two values 0, 1, 0, 1, 0, 1, that is binary. What is expected value of AI? It is nothing but value of AI, that is 1 into probability ith unit included in sample, plus another value of AI is 0. Probability ith unit does not include in the sample. 0 multiply any probability is 0. So you have only first answer. We proved the inclusion of specific unit in the sample previously n upon n. And that is why expected value of AI is n upon n, which is written by me in this expression, you can see expected value of AI is n upon n. That is the reason. Now, what is the next? Expected value of AI square. AI take value 1, 0. So, AI square also take value 1, 0 because 1 square is 1 and 0 square is 0. So, expectation of AI square is again n upon n. Now, what is expected value of AI aj? Now, AI is 1, 0, aj 1, 0. So, this product will be again 1, 0. But when it will be 1? If ith element, jth element, both are coming in sample. Otherwise, the product will be 0. So, this is expected value of product is 1 multiply ith unit as well as jth unit included in sample. Now, suppose I speak for ith unit. Under without replacement, chance of including ith unit is n upon n. Now I speak for another unit. Method is without replacement. So sample size to be selected is n minus 1 and population has n minus 1 values. So this is the probability for zth unit and this is the probability for ith unit. Multiply 1 gives expectation. So it is the expected value of product. Now consider variance of y bar under without replacement is variance of summation yi upon n. This n is a constant, will be taken outside as a square, variance of yi. This is written in the terms of population quantity. The procedure will be continued, but this approach is by another way. You have variance of y bar under without replacement, expected value of y bar. You can go by this approach, doesn't matter, you will get the answer. Expected value of y bar square minus square of e by y bar. This we proved. Expectation of sample mean is a population mean, square of that. Expected value of summation yi upon n square taken out, summation I1 to n ai yi whole bracket square minus y bar square. 1 upon n square outside, expectation of this quantity. Now you can see this is sum of square will be written by this way just like previously we do. Here I say I less than j. If I say I not equal to j, these two will be cancelled. Just like x plus y whole square of x plus square of y plus 2 times xy. So this is 2 coming if you say I less than j minus y bar square. Take expectation inside. It goes only for indicator variable because after putting indicator, this become constant, this become constant. So E of AI square, E of AI is a, and continue. E of AI square is n upon n. E of AI is we derived n into n minus 1, capital N into n minus 1. So this constant taken out, remaining as it is. This constant taken out, summation I less than j, yj, no change. Here no change. Now this is sum of product. Just like I explained before, it is written by this way. Square of sum minus sum of square. Just now we have discussed. Minus y bar square. So this n upon n, this n upon n will be taken out. So curly bracket for this plus curly bracket with these coefficients. I multiply this inside minus y bar square. This is the derivation you have to keep in mind, go step by step and see the simplification. Sum of yi square and here sum of yi square. If I take a comma, it will be 1 minus this quantity plus this as it is. Sum of yi is n time y bar whole square minus y bar square. Sum of yi square, this 1 upon n square there. This everything will be simplified. You drop this 1 upon n square from here, n upon n square sum of y square plus n into n minus 1, n time n minus 1, sum of y whole square minus sum of square minus y bar square. If you simplify this, at the last, your expression will come like this. You take the page and try to derive this one by one. If you have doubt, you can discuss with me by coming at any time to the college. So this is your simplification. Sum of yi square minus n time y bar square is nothing but summation yi minus y bar whole square, and that is written as n minus 1 s square. So this n minus 1 cancel with this n minus 1. Finally, I reach my derivation variance of y bar under without replacement n minus n small n divided by n into n s square. Keep in mind this expression under without replacement and see what is variance of y bar under with replacement. Very small change, that change is here. Here it is n minus 1 under with replacement. Other quantity same. If I do by without replacement, it become capital N minus small n. That is the change to be remembered. Otherwise, both formulas are similar. That change is coming in the picture. If I want standard error, just take the root of this quantity. That will be standard error of sample mean under without replacement. I put certain remark. We write variance of y bar without replacement. This expression can be simplified like this. S square by small n and this divided by capital N. Capital N by capital N is 1 minus small n divided by capital N. Let f is a correction factor called as a sampling fraction n upon n. So this is 1 minus f s square by n, where 1 minus f is known as finite population fraction. That means if population is very large as compared to sample size, this factor becomes 0. So 1 minus 0 is 1. So your variance of y bar for large population is S square by n. Same thing happening for width replacement. Under width replacement, if you find the case, n comes here, S square by n divided by n is 1 minus 1 upon n. If n is very large, 1 upon n becomes 0, 1 minus 0 is 1. So, if you consider population very, very large, variance of y bar, approximate variance for with replacement and for without replacement same, that is S square upon small n. That is the limiting case under with replacement and without replacement. Remark number 2, that is just now I said, if population size is large and sample is considerable very small, then f goes to 0, 1 minus f goes to 1 as n goes to infinity. So, variance of sample mean approximately S square by n in both sampling, and standard error is root of this.